So here, Tree wants to start a little chocolate business, and to attract more customers, he decides to package his chocolates in a little novelty packaging. This is the basic diagram of the packaging concept he has thought of: a large cuboid with a cuboid-shaped hole in the center. Now there are 3 different types of sides. Here's the one at the top and bottom with the hole in the center. 4 of the orange shaped sides, which are on the outside, and 4 of the blue shaded sides, which are on the inside. And all of these add up to make the surface area, which is handful for our first question. Show that the total surface area, a centimeter square, of the box is given by a equals 16x squared plus 4,000 over x. Now first, let's calculate the surface area in terms of x and h. First here is the orange one. This one of these is 3x times h. So 4 of these should equal to 4 times 3xh. Plus these ones. One of these is 3x times 3x, which is 9x squared, minus the hole in the center, which is x squared. So that equals to 2 times 9x squared minus x squared. And last but not least, these blue shaded ones on the inside, which one of these is equal to x times h. So 4 of those equals to 4 times xh. We simplify that into 12xh plus 4xh plus 16x squared. And we get this equation, which is still in terms of xh, which is 16xh plus 16x squared. But if you see in the equation right here, there is no h. So we still need to evaluate the h. Now, from the volume, we know that the volume is 2,000 centimeter cube. We know that the volume is this large cuboid minus the small cuboid inside. The large cuboid's volume is given by multiplying 3x times h, which is 9x squared h. And the smaller cuboid's volume is given by multiplying x by h, which is x squared h. So we evaluate that, and we get 2,000 equals 8x squared h. And since we are finding the h, we isolate it, and we get h equals 2,000 over 8x squared. Next, we have this initial equation we had before, and we'll replace the h with the value we got before. So 16x squared plus 16x times 2,000 over 8x squared. And we can do some crossing out, and our end result is 16x squared plus 4,000 over x, which is the same as the value or equation in the question. Next. So Tree is worried a little about manufacturing costs and how big the surface area is, because the bigger the surface area, the more Tree will have to spend for packaging material. So let's find the minimum amount of surface area needed for this type of packaging to still fit the 2,000 centimeter cube volume and all the other requirements. Now, to do this, we must find the minimum value of a. And if you remembered from the website, we can find minimum and maximum values through the use of second derivatives. First of all, we have the equation we got from before, and let's turn it into a simpler function. A of x equals 16x squared plus 4,000 x to the power of -1, which is basically 4,000 over x. The derivative of this is 32x minus 4,000 x to the power of -2. Now, what do we do with this? When searching for the maximum and minimum, we have to keep in mind that the gradients of the points that are the maximum and minimum are always 0. And so since here we have the gradient function of this function, we must find out what x value gives us 0. And so we equate the derivative with 0. We further evaluate it, and we end up with x cubed equals 125, which equals to x equals to 5. So when x equals to 5, the gradient of that certain point is 0. But then, how can we tell if this is the maximum or the minimum, since it's not stated? This is where the use of second derivatives come in handy. So we have the derivative from before, and we find the second derivative, which is the derivative of that. And that is 32 plus 8,000 x to the power of negative 3. Now what do we do next? We input x equals to 5 into this second derivative. 32 plus 8,000 times 5 to the power of negative 3 equals to 96. Now we can tell whether this certain point is the maximum or minimum to see if it's less or more than 0. 96 is greater than 0, which indicates that x equals 5 is a local minimum. Meanwhile, if the results from this was less than 0, that would indicate that the certain point is a local maximum. But in this case, it's a local minimum. And finally, we substitute x equals to 5 into our initial function. So a of 5 equals 16 times 5 squared plus 4,000 over 5. And that gives us 1,200 centimeters squared, which is our minimum value of a. And to prove this even further, if we input this into a graphing calculator and find the extremum, which is basically the minimum and maximum points, we find that when x equals to 5, y equals to 1,200, which is an extremum. That proves our point.